Alright, so today we are looking at semi-simple and nilpotent. Never sure how to capitalize these here. Elements in semisimple Lie algebras. Bit of a long title today, that's how it goes. And as always, as usual, not always, we start out with a proposition. Let M be a finite dimensional. No, we're writing things out today because another video where we gotta go things a bit slower. It's going to be a finite dimensional vector space over K, and G is going to be a semisimple. It's going to be a subalgebra of the general linear Lie algebra of M. Then G contains the semisimple and nilpotent components of its elements. And what's our proof? Saw before, if K1 extends K in the classic Bourbaki manner, then the killing form, we saw that the killing form of G1 of the extension of G, GK1 extends that of G is the extension to GK1 of that of G, and hence is non-degenerate. Therefore, the extension of GK1 is semisimple. Thus, we can we will be working when K is algebraically closed. Okay, so for every subspace n of m let Gn be the subalgebra of the general linear Lie algebra of M of elements which leave n stable and whose restriction to n has trace of 0. As we have that a semi-simple algebra is its own derived algebra, we have that G is going to be contained in Gn if, not is, if n is stable under G. So we're going to let G star be the intersection of the normalizer in GLM of G and the algebras where n runs through the set of subspaces of M stable under G. As the semi-simple component, and we're doing this with the semi-simple and the nilpotent component. The semi-simple component is S and the nilpotent component is N of X in the general linear Lie algebra of M is, we saw, a polynomial in X with no constant term and that the adjoint of X, of course respectively the adjoint of N, is the semi-simple, alternatively the nilpotent, component of the adjoint of X, which we have seen before, then X being in G star implies that S in G star and N is in G star. Thus, we're going to show that G star is just G. Since G is a semisimple ideal, of our G star, we can find an A such that G star splits into the direct product of A and G. Let A hat be in A, and we're going to let N be a subspace which is minimal among the non-zero subspaces of M which are stable under G. The restriction of A hat to N is a scalar multiple of the identity. This is, of course, by Burnside's theorem. It has trace 0 by definition. And hence is 0 as the characteristic of our field K is 0. As M is the direct sum of subspaces such as N, we get that A is 0 and that G star is just G. Let me check real quick to how far we've made it. Okay. So up next, we have a corollary of this, which states that an element x of G is semisimple, or alternatively is nilpotent, as an endomorphism of M if and only if the adjoint in G of X is a semisimple, respectively nilpotent, however you want to say it, endomorphism of G. Let's look at our proof. We are going to let S, or alternatively N, be the semisimple, of course going to be respectively the nilpotent components of X in G. Then from above, we have S in G and N in G. Then the G adjoint of S, or the G adjoint of N, that's not how you write that. The G adjoint of N is the semisimple, once again, the semisimple, or respectively the nilpotent component of the G adjoint of X by a previous result, if X is semisimple, respectively nilpotent, so is the adjoint in G of X. And so the G adjoint of X equal to the G adjoint of S, or alternatively the G adjoint of N, alternatively. And so X equals X, or X equals N, since the adjoint representation of G is faithful. This motivates the following definition. We're going to let G is going to be a semisimple, sorry about that, be a semisimple Lie algebra an element x in G is semisimple, respectively nilpotent, if for every G module M of finite dimension on K, we have that the representation of X is a semisimple, or alternatively nilpotent, endomorphism of M, of course. All right, we have another proposition here. We're going to take two semisimple algebras, we'll call them G and G prime. These are semisimple, they're Lie, and they are algebras. And F, a homomorphism of G into G prime. Into, so this one isn't surjective necessarily. Fx in G is semisimple, and of course respectively nilpotent. So is f of x. If f is surjective, then every semisimple respectively nilpotent element of G prime is the image under F of a similar image that is likewise going to be semisimple or nilpotent element of G. Our proof. If rho is a representation Rho is a representation of G prime. Its composition with F is a representation of G, of course. So that gives us our first assertion, which is that X preserves the semisimplicity and nilpotency of elements in G. When F is surjective, there exists a homomorphism. I don't know why they're so obsessed with using the same letters for different things. I'm going to call it G hat of G prime, and it's going to send G prime into G such that its the composition of F with G hat is the identity of G prime. And so our second assertion. Since we can just send everything over back to G and get it back. And I think we're going to close off this video with a theorem, so maybe this will be a bit of a shorter one again, but that's kind of how things are pacing themselves here, today at least. Our theorem. Let G is going to be, as you'd expect, a semisimple Lie algebra. There's two parts. A. First off, we're going to let X in G if there exists. So if we can construct a faithful representation, which we are, as always, going to call rho of G, such that rho X is a semisimple, or once again, alternatively, nilpotent endomorphism then X is semisimple, or once again, alternatively, nilpotent. Condition B, part B. Every element of G, this is a good theorem actually to close on. Every element of G can be written as the sum written uniquely as the sum of a semisimple element and a commuting nilpotent element. And by that I mean that we can write it as a sum of a semisimple element and a nilpotent element, and those two elements commute with each other, and that that sum is unique. And the proof. First off, we're going to suppose A. Let sigma be a representation of G B is going to be the supplementary ideal of the kernel of sigma, and we're going to let alpha be the projection of G of G onto B. Wanted to see from it if that was H, because the font they're using, it's some kind of like Frankfurt looking font. Then we have that the adjoint of X is semisimple, respectively nilpotent, by our corollary. And hence, so is the adjoint in B of the projection of our X onto B, as sigma of X is equal to sigma of alpha of X we get A from our corollary and B from our first proposition of today, this video at least. And that proposition applied to a faithful representation. Alright, so that's, I guess that'll be it for today. Hopefully, I kind of scheduled things bad today, and tomorrow something might be happening, so we might only get 2 videos tomorrow, but I guess we'll have to see when we get there, right?